You can start them over. Now I have to begin with a word of prayer again. Heavenly Father, we thank you for this day, and I thank you again for these students. Lord, in your name I pray, Lord Jesus. Amen. All right, so definition. Let V paired with the inner product be an inner product space over F. Again, it's either the reals or the complexes, right? Then we say that X and Y in V are orthogonal, all right? If and only if the inner product of X and Y is equal to 0. We write, in this case, we write X perpendicular to Y, all right? So we'll also call X and Y perpendicular, all right? So if you have a subset of the vector space, all right, and X, Y in the subset implies that X is perpendicular to Y, X equal to Y implies that X is it's funny because the grader was here like 5 minutes ago, but and I said what was going to happen if somebody brings the homework in 5 minutes from now, and then so we agreed that she would pick it up on Sunday, so it's all good. So
and then I just pop in.
Yep. I mean it's fine. So I was trying to get the grader to pick it up like an hour from now because I thought that it was likely that there was one more coming. But graders will be graders. What can I do? Okay, so the condition that X is not equal to Y here is just to avoid well, I'm not sure why that's there, honestly, as I think about it. But anyway, it's there. I was smarter when I wrote these notes, so let's leave it there. So if S, a subset of V, is orthogonal, all right, and each X in S has norm of X, and we're still talking about the induced norm, okay? So inner product of square root of the inner product of X with X equal to 1, then S is what? Yeah, orthonormal. So hopefully we talked about these things in Math 221, but there we were just talking about it in the context of the inner product being the dot product, right? So that discussion basically now needs to generalize to a more abstract inner product. An orthonormal basis is a basis. Now hold on, this is really going to be surprising, which is orthonormal. Likewise, we could define, orthogonal basis. Orthogonal basis is an orthogonal, is a basis which is orthogonal. All right. So I wanted to start here today. Now, so our next proposition is oh man. Oh yeah, okay. So if z is equal to x plus y, where x is perpendicular to y, then the length of z squared is equal to the length of x squared plus the length of y squared. All right. So let us see if we can prove that. All right. All right. So here's the proof. And of course the context is, you know, we're in an inner product space, right, with induced norm. So let x comma y be in V with z equals to x plus y, and suppose that the inner product of x and y is equal to 0. Then the length of z squared is the inner product of z with z, right? Which is the inner product of x plus y with x plus y. And this is going to look a lot like, you know, the calculations we did in the proof of the triangle inequality, right? It's like that calculation all over again. So this is inner product of x and x plus the inner product of y with x plus the inner product of x with y plus the inner product of y with y, right? I guess a more basic theorem I should have probably proved, like lemma, whatever you want to call it. X is perpendicular to y if and only if y is perpendicular to x, right? And the proof of that basically is what? xy equals to 0, then the yx is equal to the conjugate of xy, which is the conjugate of 0, which is equal to 0. So we can't have the inner product of x and y be 0 unless we also have the inner product of y and x be 0. So good news. X is perpendicular to y if and only if y is perpendicular to x, which is a comfort. So as such, we have this is 0, this is 0, and we've got norm of x squared plus norm of y squared, and we're done. All right? So that brings us to the, the more systematic study of orthogonality. And I want to talk about our standard examples and, is the standard basis orthogonal, right? So let's study that. So examples. Example 1, I suppose. Rn with, dot product, notice that we have EI dot EJ, right, is, that is the inner product here, right? But anyway, it's Kronecker delta IJ. By the way, Kronecker delta IJ is what we want for an orthonormal basis, right? Notice that this means that EI dot EI is equal to 1, which says that the length of EI is equal to 1 for all I. And also, of course, EI dot EJ is equal to 0 for I not equals to j, right? So we have the normality as well as the orthogonality. So we have an orthonormal basis. The standard basis is orthonormal. Now, example 2, talk about Cn, right, with the inner product of Z and W being Z transpose times W conjugate, right? Again, EI, EJ is equal to EI transpose EJ conjugate, but these are real vectors, so the complex conjugate is, easy enough to miss. This is EI transpose times EJ, which is again Kronecker delta IJ. So yes, the standard basis for Cn, which is orthonormal with respect to the usual Cn basis. What about the matrix units? We can think about R, Mn, my bad, M cross N, right? It's the span of these things, right? Eij such that 1 less than or equal to I less than or equal to M, 1 less than or equal to J less than or equal to N, right? The standard matrix unit basis. And I do want to think about the case that these are rectangular. All right, so if they're rectangular, I really should probably use different letters for M versus N, right? Like, what I'm trying to say is, let's think about our M as like the span of, let's say F1, Fm, right? And we'll use our usual notation for Rn. Right? And so how do we build Eij in this system of notation? I mean, this is how many rows, how many columns here? Rm is what? 1 column, M rows, right? So this is M by 1, M as in mommy, N as in nanu. And this, of course, is Rn by 1. So I'm trying to build a M by N matrix here. Which one do I have to put first? I got to put the F first, right? So I got to go Fi times E J transpose. So that makes sense, see, because this is an M by 1 times a 1 by N. So that's an M by N matrix. This is how we can build the matrix units from the standard basis. Question? No, just a certain amount of. You guys look, your looks. I don't know what to say with the, Listen, so we can check that this makes sense with some calculation, right? Supposedly, if we calculate if we calculate EIJ, the k-th component, that should, work out to a certain thing. Let's see if it does. So the way to do that is I do, so I have to do F sub k transpose on the one side, and then I've got my Fi Ej transpose, that, and then times EL. So multiplying a matrix by the transpose basis on the left and the column basis on the right is a simple way to select the k-th component, right? Multiplying on the right by the standard basis gives us the th column. Multiplying on the left by the transpose of the kth basis gives us the kth row. And if we calculate the kth row of the th column, that's the KL component. Yeah? But look, these, what is that? That's nothing more than the dot product of this and that, which gives me a Kronecker delta Ki. And this is the dot product of Ej with El, which gives me a Kronecker delta JL. But that is exactly our definition of the matrix unit. Namely, it's the matrix which is 0 everywhere except for the ijth component where you have 1. All right? So there you go. That's the matrix unit. Just a quick review. Does the matrix unit give us an orthonormal basis for R m by n? So remember that we defined the inner product here to be the trace of AB transpose. All right, that was our definition of inner product here. And so the question is, if I do Eij, comma, EKL, what happens? All right? So it's the trace of Eij times EKL transpose, right? And at this point, I'm going to use my, my construction of it. So that's like F sub I, E sub J transpose, and then I have sock shoes, right? So, oh fine, I'll write it down. F sub K, E sub L transpose, that gets transposed. All right, so that's the trace of what? We got trace of Fi, Ej, transpose, and that gives me EL, right? And then FK transpose. Transpose is, undone. It's gone. Transpose of the transpose is just the thing again. All right, so in the middle, we have the trace then of Kronecker delta JL times F sub I, F sub K transpose. Right? So I can, linearity of the trace, I can pull the Kronecker delta up front, Kronecker delta JL of the trace of, now what is this? What is Fi times Fi transpose, by the way? Fi times Fk transpose. Let's think about that. That's a m by 1 times a 1 by m, right? So this is an m by n matrix, right? So this is, how does that matrix work? What's it look like? It's mostly zeros, right? except what? It's got a 1 where? The ikth spot, right? So how does this work out? This is Kronecker delta JL times what? 1 if I equals to k, 0 if I is not equal to k, right? Do you see why that is? The trace adds up the diagonals, right? So the only way that there's a 1 on the diagonal is if I is equal to k. Otherwise, the trace is 0. So that's what the trace of this matrix is. It's that. But what is that? Well, that's Kronecker IK, isn't it? So what we have is Kronecker delta JL, Kronecker delta IK. Let me write it up here. So we just showed, after a little bit of work, that EIJ, and there's probably an easier way to show this. This is just the way I did it today, guys, right? Kronecker delta JL, Kronecker delta IK. That's the result we just found. So does that give us orthonormality? So if these are distinct, right, that means that at least one of the index pairs, either the row with the row or the column with the column, disagrees, which then means that either this one, which is based on the column index, or this one, which is based on the row indices matching, is 0. Therefore, if these are distinct, the inner product is 0, which is to say they're orthogonal. Are they length 1? Well, if I is equal to k and j is equal to l, that makes them the same, and that makes this equal to 1 times 1. So yes, the matrix units are orthonormal with respect to the usual. This is called the Frobenius inner product, for what it's worth. And the induced norm is also known as the Frobenius norm here. All right. So there's that. Do you guys have any questions before I go on? All right. I've forgotten about the danger of the sprayer. If you're not careful, it's easy enough to walk into that cloud of spray. And there's no good part of it. It's not good for your eyes. It's not good in your nose, and it definitely doesn't taste good. None of the above. I'm not sure what it does for hair. So example 3. And of course, I won't go through it, but by the way, complex matrices, almost the same argument. The matrix units are also an orthonormal basis for CMN. Okay. But this one here is really different. P2R, right, is with basis, the usual monomial basis, right? Beta 1x squared. If we calculate the inner product of 1 with 1, or the inner product of x with x, or the inner product of x squared with x squared, all right, what are those? So what's our inner product? Well, I should probably tell you that, huh? So our inner product here, we're going to define the inner product of f and g to be the integral from -1 to 1 of, let's say, f of x, g of x, dx. This defines the inner product. Well, this defines a inner product on polynomials. There are always other inner products to use, right? So if I say the inner product, it's just because I'm being careless. There's always an infinity of choices for the inner product. But here's the one we're going to use. So you guys, you can do the integral. What's the integral? So we're looking at what? Integral -1 to 1. You thought you were safe from integration in this course. Well, think again. Haha. So that's 2. this is the integral from minus 1 to 1 of x squared, also known as 2/3. This is the integral from minus 1 to 1 of x to the power 4, also known as 2/5. All right. And so this means that the length of 1 is what? It's the square root of 2, right? The length of x is what? It's the square root of 2 over 3, actually. The length of x squared here is, the square root of 2 over 5. So this basis is definitely not normal, right? Not a normalized basis. But guess what? It's not even orthogonal. Because if we calculate the inner product of, say, 1 with x, what do we get? Oh, wait a minute. This is an odd function integrated about we could actually do the integral, right? X squared over 2, evaluated from minus 1 to 1, you get 0. Oh no, maybe it is orthogonal. Oh man, look at that. And what about x with x squared? Well, that's integral from minus 1 to 1 of x cubed, which, well, that's also 0. Wait a second, maybe this is orthogonal. I'm just joking, it's not. Which one's not going to give us 0? It just takes 1 to spoil it, right? How about 1 with x squared? Well, that's 2/3, right? That's x cubed over 3 evaluated from minus 1 to 1, which I've been just glibly writing as 2/3. So this basis is not orthogonal. All right. Now, so here's without much more computation, I can give you an orthogonal basis for P1R if I was to use, say, gamma equal to 1 over the square root of 2, right? And let's say x over what? X over the square root of 2/3, right? This would be orthonormal. Basis for, P1R. So there's that. Any questions? No? All right. Do you guys have any ideas how could we fix the basis and come up with an orthonormal basis? What would we do? How did we fix it in 221? How do you take yeah?
Did you calculate, you calculated the magnitude and then took the reciprocal of it and then normalized it that way?
That's the normalization. That's what I did here.
Okay.
That's part of it. But how do I make it orthogonal? Some algorithm? Yeah. I think you're on the path. Yeah. The Gram-Schmidt. Yes, we use the Gram-Schmidt algorithm, which we'll get back to here. Maybe not today, but that's like one of the next things coming up. So we'll see that the Gram-Schmidt algorithm, it does in fact apply here. So this was an example that we had last time, right? These set of complex valued continuous functions, remember? And so the well, I'm not going to talk about a basis here, but I'm going to let S be a set of things of the form EINT, such that n is a natural number. All right. So note that the derivative with respect to t of e to the INT is in e to the INT. That's how that goes. And so the integral of e to the int dt is actually 1 over in e to the int plus a constant. And so if we calculate the inner product of e to the m as in mommy, e to the int, n as in nenu, our definition for inner product here, I'll remind you, was 1 over 2 pi, and then we integrate from 0 to 2 pi, and we do the first function times the complex conjugate of the second one. All right? And here, so I got 1 over 2 pi, the integral from 0 to 2 pi of e to the n minus m times t dt. Because the complex conjugate of e to the imt is, well, that's cosine mt. If you guys are wondering, I mean, I did talk about this before, I think, but I'll talk about it again. So e to the imt means this, right? And so when we take the complex conjugate of that, we get, cosine mt minus I sine nt mmt, which, because sine is odd and cosine is even, is e to the minus imt. Complex math is very forgiving. Like this idea, to do complex conjugation, you just switch out I with minus I. It's amazing how much that just works with the notation. So, all right, and then this is equal to 1 over 2 pi times 1 over n minus, I times n minus n, right? E to the I times n minus m t evaluated from 0 to 2 pi. Yes, calculus of complex valued functions works just like that, if you're wondering. Now here I'm assuming what? Once I write that, what have I assumed? Right, n is not equal to m, otherwise we're dividing by 0, right? But what is this? This is 1 over 2 pi. 2 pi I times n minus m, right? And then we've got e to the 2 pi I times n minus m minus, e to the 0. But what happens when you plug in a 2 pi good if I can't use words, a integer multiple of 2 pi into cosine and sine is what? The sine is 0, the cosine is 1, right? So this is 1, and this is 1, and we get 0. On the flip side, if we do e to the imt, e to the imt, right? We get 1 over 2 pi, the integral from 0 to 2 pi of e to the imt, e to the minus imt dt, which of course is just the integral 1 over 2 pi times the integral from 0 to 2 pi of dt, also known as, 1. So in summary, e to the imt, e to the int is equal to the Kronecker delta mn. So S is, in fact, a orthonormal subset of H. All right? It is an orthonormal subset of H. Any questions? No? All right. So that brings me to my next proposition, which is really, like what this proposition says, super important, and also a joy to prove. So it's one of those nice ones that once you understand it, You know, some things you learn how to prove, and it's still going to take a certain amount of memorization or something to really just stick it in your brain, right? We've experienced this, right? Like some of you have taken geometry, right? So we're taking geometry? No? Nobody? Geometry? Are all the proofs natural in there, or do you have to like memorize a bunch of stuff? Memorize a lot, right? If you don't have that idea about how to write the picture to start with, to start the construction, you kind of get lost. And here, you ask me to prove the Cauchy-Schwarz inequality off the top of my head, I'd probably get lost. I mean, like I have a clunky computational proof I can give, but the thing I did last class, you know, that's slick, and that's not something I have to look that up. That's not my proof. But this right here is something I think that would stick with you. So we have V with the inner product, and suppose S V1 V2 Vk is a subset. Well, not a subset. Is a set of non-zero orthogonal vectors all right. Number one, S is linearly independent. Number two, if X is in the span of S, then X is equal to the sum I equals 1 to K of X with inner product VI divided by the inner product of VI with VI, all times VI. And number two, listen to me. Number three, if S is orthonormal, and X is in the span of S, then X is equal to the sum I equals 1 to K of X with VI times VI. All right. So let's prove it. Let's prove it. So how do we prove a set is linearly independent? Well, first of all, let's state our assumptions. Assume S is a non-zero orthogonal set, right? Proof. Assume S equals to V1 through Vk is non-zero and orthogonal set. I probably should have an A there grammatically. Is a non-zero and orthogonal set. Okay. Of vectors. All right. Suppose that C1V1 plus C2V2 plus CKVK, right? Which, by the way, let's be civilized. Let's use a summation notation. The sum I equals, I'm going to use a J. Sum J equals 1 to K of CJ Vj is equal to 0. All right? Thus, the inner product of the sum J equals 1 to K of CJ Vj with Vi, all right, is equal to the inner product of 0 with Vi, right? Do you guys follow? What did we do last class, though? You guys remember? We proved that proposition, right? We did that induction proof, remember? And we have earned the right to pull out that summation and those constants. And what do we got? The sum j equals 1 to k of Cj with Vj comma Vi, and that's equal to 0, right? Notice, though, orthogonality, right, gives that the inner product of Vi with Vj, or I can do Vj with Vi, that's kind of what I did here, is equal to Kronecker delta Ij. Is that true? Not quite, right? I mean, when I is not equal to j, the formula is legit, because if I is not equal to j, they're distinct. The inner product is 0 because they're perpendicular, right? But if I is equal to j, then we're talking about the length of Vi squared, right? So I should do this times the length of, like, well, I'll write it in terms of the inner product, but it's the inner product of Vi with Vi, right? Okay, so thus, or I'll use a hence. I haven't used a hence yet. I feel smarter. So the sum j equals 1 to k of Cj times the Kronecker delta Ij of the inner product of Vi with Vi is equal to 0. But what does that tell me? Remember, the Kronecker delta is the natural enemy of the finite sum. I is a free index here. All that lives is the ith term. So we get Ci times the inner product of Vi with Vi, right? Equals to 0. But that tells me that Ci times the length of Vi squared is equal to 0, which tells me that Ci is equal to 0. Hence, I'll say thus, C1 equals to 0, C2 is equal to 0. They're all 0, right? Ck is equal to 0, and so S is linearly independent. Why? Let me write it down. Remember, we have that Vi not equal to 0 implies that the length of Vi is not equal to 0. That's how I get that the coefficient is 0. That assumption that Vi is non-zero is mission critical here. If I hadn't, this little detail right here matters quite a bit, because if you have 0 in the set, it's not linearly independent, right? 0 is there, it's dependent. But there you go, linearly independent. And almost the same calculation proves part 2, right? Let's work it out. So if x is in the span, we have what? We have x in the span of S implies that x is equal to the sum. Let's say I'll say j equals 1 to k of Cj Vj, right? The difference now is that we're not saying 0, we're saying x, right? But the calculation is very, very similar. What are we going to do? So we're working on the proof of 2 right now, right? How about take the inner product, right? Thus, the inner product of x with vi is equal to the inner product of the sum, j equals 1 to k of cj vj with vi, right? Which is equal to, by the previous class period's proposition, sum j equals 1 to k of cj inner product of vj with vi, which is equal to the sum j equals 1 to k of cj with z Kronecker delta ji of the inner product of vi with vi. But that, of course, is just ci times the inner product of vi with vi. And so we've got that x with vi is equal to that. Therefore, ci is equal to the inner product of x with vi divided by the inner product of vi with vi. Therefore, x is equal to the sum I equals 1 to k of the inner product of x with vi divided by the length of vi with vi, inner product of vi with itself, all times vi. And I just switched the I to j for the final formula because that, I think, is how I wrote it in part 2. Yeah. There you go. That's the proof of 2. How do we prove 3? Three follows immediately, since S orthonormal means the length of vi, which is equal to the square root of vi with vi, is equal to 1 for all I, 1 through k. Consequently, the inner product of vi with vi is what? It's just 1, right? It's just 1 here. In the case 3, so the formula and 3 follows. The importance of 3 cannot be overstated. I mean, this is wonderful news. It says that if we have an orthonormal basis, we can select the coordinates of the orthonormal basis simply by calculating inner products of the vector with the basis. That is really, really cool, you know? So the next thing we're going to do, next class, is to write down the Gram-Schmidt algorithm. And it's the same as it was before. It's just instead of having dot products, now we have to do inner products. And we have to be careful in the complex case because the complex conjugation issue is there, and sometimes it's an issue. But you know, if we're careful about that, then everything else is pretty much the same old song and dance. But anyway, so that's it for today.
Thank you.
Now,